We're going to work another example problem with two lenses and ask what's the overall image that's formed from this two-lens system of a distant object. In this case, there's going to be one oddity, or one introduced new complexity to the problem, and that is that sometimes object distances can be negative. So we've always heard that the object distance p is positive in any sign convention. There's one and only one case where it can be negative, and I'm going to show it to you in this kind of problem. Let's suppose an object is a distance 40 centimeters in front of a two-lens system. The first lens has a focal length of 20 centimeters, and the second lens has a focal length of 5 centimeters. If the two lenses are 25 centimeters apart, where is the final image? We're again going to take the problem in steps, and we'll first see what happens with the first lens. So we have an object out there in front of the first lens, a distance of 2 focal lengths away. Here, the focal length of that first lens is 20 centimeters, and the first object distance is a positive 40 centimeters. So there's P1. It's a positive number because it's out in front of the lens. And F1, again, is a positive number because it's a converging lens. We're going to use our usual equation, 1 over P plus 1 over I equals 1 over F. And with that reduces to I equals PF over P minus F. If P1 is plus 40, F1 is plus 20, I invite you to calculate that plus 40 centimeters is the distance I1. That means that the image is going to be real, and it's formed to the right of the objective lens. It's way over there. So there's image number 1. Since it's real, it's inverted. And I haven't said anything about what the magnification is yet, but we can come to that in the future. The eyepiece lens is 25 centimeters from the objective lens, so we said that in the statement of the problem. That's actually not as far over as where the image is. Here's the funny thing. The light source for the second lens is actually behind the second lens. Whoa. So it has actually a negative object distance of minus 15 centimeters. Remember, I1 was 40 centimeters, but the second lens was only 25 centimeters from the first lens. So that means that the image number 1 is a negative 15 centimeters away from the second lens. Here's the only time where we'll ever have a negative object distance. It's this case where you have a multiple lens system and one of the images gets thrown behind the second lens in the system. That's the only time this can happen. Usually P becomes positive in our sign convention, and in fact the previous examples we worked, even with a two-lens system, P was positive because this first image actually landed in between the two lenses. But this case, image number 1 landed beyond the second lens. So that's the light source for the lens number 2, and we have to use a negative number for P. So there's P2 right there. And the second lens has a focal length of plus 5 centimeters. We were told that. And we again use our usual equation, 1 over P plus 1 over I equals 1 over F, but we have to use now our negative number for P and our positive number for F. If we do that, we find that I2 comes out to be a positive number. It's plus 3.75 centimeters. That means it's over to the right of the lens, and it's a real image. That means it's going to be inverted relative to its light source. So image number 2 will be flipped up back above the axis, and it's a positive distance, which means it's over to the right of that second lens.